What's up, everyone? Today we're going to do a problem where we're going to take a matrix of ones and zeros and we're going to try and find the largest submatrix of that is square and is made up of all ones. So if we look at this example that we have a matrix of size 3 by 4 and we have obviously made up of ones and zeros, and the largest submatrix that we have that's square and made up of ones is either this one, or this one, and all of those are of size 2 by 2, and so our result is 2. So let's go ahead and dig into this problem, and the first thing we want to do is ask any questions that we might have of our interviewer. So really what we want to do is just make sure that we clarify the problem. So we talked a little bit about this already, but our result is going to be the size of the square matrix. So we're not going to return the actual matrix itself, and we're not going to return the total number of elements in the matrix or anything like that. We're going to return the length of one side of the matrix. But if your interviewer doesn't tell you that, that would be a good thing to clarify. Another thing that we might want to ask about is what are the actual elements of this matrix, because in this case clearly I'm using some sort of numeric value, but potentially, for example, if you were in C, you could use Boolean values because those are just represented by ones and zeros, or even in Java you could use Boolean values and just replace ones with true and zeros with false, and that might make a lot more sense because it would take up less space. Or you could use bytes, or you could use shorts, or you could use any sort of value that you want, but in this case I'm going to use integer values, and that's going to, I would want to make sure that I am either checking my input or I know that I'm going to get valid input in. So because I could potentially have values other than 1 or 0 in my array. So in this case I'm going to assume that I have a valid input array, and I'm not going to worry about checking whether all of the values are zeros or ones. But so let's actually think about now how we could potentially solve this problem. So a simple approach that we could take would just be a brute force approach, and we could do that, we would just go through all possible submatrices and all possible square submatrices and check whether they're made up of all ones. And so that would be, not great in terms of time. We could potentially write a function that would, check for each matrix and check whether all of the values were 1 or not, and so the code wouldn't be too difficult, but in terms of time it's going to be pretty slow because so in this case we would have to go through all possible submatrices. So like if we look at a example, just like this is not a very interesting example, but just to get a sense for what the time complexity would be, and looking at a square matrix is going to make this a little easier. We're basically going to we're going to go through the largest possible subarray, which is there's going to be one subarray of size 4, and then there are going to be 4 subarrays of size 3. So there are those 2 and these 2. So that's going to be 4, and then there are going to be 9 subarrays of size 2. There are going to be 16 subarrays of size 1, right? So 9, 16, and as you can hopefully see, this is the sum of the squares of 1 to n, right? And so if we actually were to convert that into big O notation, we would get big O of n cubed. And you can actually, probably the easiest way to figure this out is just to put it into Wolfram Alpha, so you don't have to actually do the math yourself, but you get n cubed. So that's not really that great, and that's only the number of submatrices. That's not even counting us having to go through and, actually check whether each submatrix is of all ones or not. So we would like to do better than this, and we can potentially do better than this by using dynamic programming. And so what we want to think about here is that we always know we can figure out whether a specific cell is part of a larger square submatrix by looking at the surrounding submatrices. So let's take an example. So we'll just do this example, a simple example where we have a submatrix of size 3, just like this. And what I'm going to do is I'm going to go ahead and I'm going to create another array. So I'm going to create this, and it's going to mirror my original array, but it's going to represent something different. So what each of these cells represents is it represents the size of the largest submatrix whose bottom right-hand corner is that cell. So hopefully, if that doesn't make sense, this should hopefully become clear. But let's look at, first of all, we can look at the top left-hand corner. And we see this is, if we consider this to be the bottom right-hand corner of a submatrix, then the largest possible submatrix is of size 1. Because it's in the upper left-hand corner, there's no possible way that there can be any cells to the left or above it that would make it part of a larger subarray. So that's going to be 1, and the same is going to be true for any cell that's either on the left-hand side or along the top, because we're looking at the bottom right-hand corner. So if we can't go up or left, then we know that since it's a square matrix, that has to be of size 1, because we can't actually expand in either direction. So we can say that, and that hopefully makes sense when we look at it, so we say that all of these are the bottom right-hand corner of a 1x1 subarray. And then we can fill out the rest of this. So if we look here, this is the bottom of a 2x2 subarray. So that would end up being 2. This here is also the bottom right-hand corner of a 2x2 subarray because we have this subarray. So we get 2. This cell here, same thing. And then this cell here is the bottom of a 3x3 subarray. So this would be 3. And so if we can calculate this array, then all we need to do is get the largest value in this array, and that's going to be all that we need to do. And that's going to be pretty simple, and that's going to take, if we can calculate each cell in constant time, then that's going to take quadratic time to solve this whole problem. And that's going to be much better than our cubic plus time that we had before. So how can we actually calculate this? And this is going back to what I said about dynamic programming. We're going to use the smaller problems to compute the results to the bigger problems. So let's imagine that we're gonna go through this and we're going to generate this array. So let's go back to the beginning and zero all these out, and we can go ahead and we'll need something to start with. So let's start with this first cell. As we mentioned before, because the top left-hand corner, we know it's 1. And basically we know that this value is going to be 1 if the value in the original submatrix or the original matrix is 1, and it's going to be 0 otherwise. And the same is going to be true for all of these in both of these, in this row and this first column. Because again, we're pushing up against the edge of the matrix. So we can just go through and say, let's traverse this from right to left and top to bottom. So we're going to, for this top row, we just say that these values are equal to the values in the original array. Then for this next one, the first value we have is the same. And then this second cell, we can look at the values of the cells surrounding it. So these 3 cells. And basically we can say that if all 3 of these cells are 1, then the current cell, if the current cell is 1, this one, the current cell would complete a larger subarray. And hopefully this will become even more clear as we go further along. But this cell, because all the ones surrounding it are 1, is going to complete a subarray of size 2. So it's going to be like the size of these ones plus 1, so 2. Because we're going to have 1 here, 1 here, 1 here, and it's basically like 3/4 of a square, right? So we're just filling in the square. And then the same is going to be true here in this cell, where we're going to get the 3 surrounding it are 1, and this one is 1, or this one is 1. So it's going to complete a larger square, and we're going to get 2. And then again, this one's 0, so if they're ever 0, we're just going to put 0 in the cell. And then we come back here, we're back against the edge again, so we set it to 1. And then this one, we're going to look to the left and the top. And in this case, we have different values. So we have a 2 above it, but we have a 1 here. And so what that means is that we have this 2x2 array here, which if we had a 2x2 array to the left of it, then we would be able to complete a larger, or if we had a 2x2 to the top left of it, then we would be able to complete a 3x3 array. But we don't, because these are only 1x1. So we have to take the minimum of the possibilities, right? So in this case, we only have 1 here and we only have a 1x1 here and 1x1 here, or 1x1 here, 1x1 here. So we have to take the minimum and add 1. And since this one's 1, we end up with 2 because it's the minimum of this array and then these 2 individual arrays. And then finally, we get to this last cell here, or that is a 1, and we see that all 3 surrounding arrays are of size 2. So we get this one, and this one. And since those are all of size 2, we've filled in all of these surrounding cells that we need to fill in to make this be the last cell. So this is now the last cell to fill out our 3x3 matrix. And so we can fill in a 3 there. And hopefully that makes sense. It's a fairly straightforward algorithm, and all we're doing is just basically going from top left to bottom right, and we're filling it in based on whether or not our cell is completing part of a larger subarray. And then all we have to do is obviously either we could go back through this at the end and find the largest value, or we could just track the largest value as we go, and then that largest value is going to be the value that we want to return. So let's go ahead and actually look at what the code would look like for this. So I'm gonna call it subarray. And obviously we're returning an integer because the integer is going to be, in this case, this 3 here, or in this case, the 2. And we are going to take in a 2D array. So we're gonna take in I'm just gonna call it R. And then, first of all, we are going to want to actually check probably that our array is not, that either dimension of our array is not 0, right? So, and I'm also going to reuse both dimensions, so I'm going to set them to variables first. So I'm going to say int x equals r.length, and if x equals 0, return 0. And then I'm going to say int y equals r.length, sorry, it's going to be equal to r 0.length. And then if y equals 0, we're going to return 0. And so, as you can see, what I did here is, unfortunately, I can't group this better. I can't do x and y and then say if x or y is equal to 0. Because if x is equal to 0, then this would fail, right? This would be an illegal operation. So I have to check if x is 0 first and then return before I can actually even get the value of y. So unfortunately, it's a little less clean. It's like a few more, it's an extra line of code, which is not ideal, but whatever. And then I'm going to track, I want to track the maximum because I don't want to, it would actually be the same time complexity to go back through afterwards and find the largest element in this subarray, or in this array, because it's going to take n squared time to do that, and it takes n squared time to actually compute this array to begin with. So it would be 2n squared, or big O of n squared time. And so it doesn't actually make a difference, but it's, you know, slightly more efficient, and it doesn't, I don't lose anything by doing it. So I'm going to just do that, and I'm going to say max equals 0. Oh, and I should mention I'm returning 0 here because if, you know, if it's a non-existent, or if it's if the either dimension of the array is 0, then obviously the largest subarray is going to be, the largest square subarray of anything would be 0, let alone 1s. And then what I'm going to do is I'm going to iterate. I'm going to create a new array that's going to be this one, and I'm going to call it sizes. I'm just going to say int sizes because it's the sizes of each subarray, and it's going to be a new int x and y. And then I'm going to do a for loop, and I'm going to iterate through this entire array, and I'm going to compute it exactly as we talked about up here. So I'm going to say for int I equals 0, I is less than x, and I plus plus. And we're doing this nested for loop, so we're going to do for int j equals 0, j is less than y, and j plus plus. And then all I need to do is say, okay, so all we need now is we're going to have a couple different cases, right? So if either x or if either I or j is equal to 0, then the value is equal to the value in the original array, right? Because we're along either the top edge or the left edge. So I'm going to start by just doing if I equals 0 or j equals 0. Then all we need to do is say that sizes ij is equal to rij. Right? So that should be fairly simple. And then the other case is going to be if it's not, if the value in rij is equal to 1. Right? Because if the value in rij is equal to 0 at any point, then we want the value in the sizes array to be 0 as well. So we're just going to ignore those cases. So if rij equals 1, then what we need to do is say, so sizes ij is going to, and remember, we're basically taking the maximum of the 3. So in this case, we took the maximum of this. So for this cell, we took the maximum of this one, and this one, and then added 1. And in the case of this cell, we took the maximum of these 3 and added 1. And so that's what we're going to do in each case. So we're going to say size ij is going to be equal to math, or sorry, actually we're taking the minimum. So it's math.min of we're comparing 3, so I'm going to nest the math.mins. So math.min of math.min sizes I j minus 1, and then sizes I minus 1 j, and then sizes I minus 1 j minus 1. Right, so we're taking the minimum. So we're taking the minimum of these two, and then comparing that to the minimum of this one. So we're taking the minimum of those 3 values, and then what we're going to do is set that to be equal to size, and then obviously also we have to add 1 to this. So we're going to do that just plus 1, and so that's going to be our value. And then finally we need to update our max, right? So we're going to say if sizes ij is greater than max, then we just say max equals sizes ij. And then all that's left is to return max. So that's our entire code for this problem, and hopefully you can see how that reflects our original algorithm that we came up with, and also hopefully it's clear that that algorithm makes sense. And let's just go through a quick example. So we can actually, let's actually just do this original example that we had here. So we're going to create this array, and then we're going to create an empty sizes array. And then let's go through this. So we're going to say that neither dimension is 0, and then max equals 0. So let's just say max equals 0. And then for I, so we're going to go through the rows first, and then we're going to say, let's see. So I is equal to 0, and j is equal to 0. So we set that equal to the value here. Then for this one, I is again equal to 0, or yeah, I is equal to 0. So we set it equal to this value, which is 1. Whoops, 1. And then again, same here. Then this one, j is equal to 0. So we're going to set that equal to 1. And then in this cell, we get that neither I or j is equal to 0, and the min of these is going to be equal to 1, plus 1 equals 2. And then we set max to be equal to 2. Sorry, we should have set it to be equal to 1 earlier, but I forgot that. And then in this case, we're going to take the min of these cells. And so the min is 1 plus 1 equals 2. And then in this, we take the min of these 3, which is in this case 0 plus 1 equals 1. And then we come down to here, we get that the min, that this is actually on the left-hand side, so j is equal to 0. So we set that equal to this value. Then this one, the min value of these 3 is equal to 1, so we set this to 2. This is equal to 0, so we skip it, and this is equal to 0, so we skip it. And so now we get that max value is equal to 2, and we return that. And so yeah, that's all there is to this problem. And hopefully that made sense. This algorithm will run in O of n squared time if it's a square matrix, or O of n times m if you have an n by m matrix, which hopefully makes sense. And also, it's going to take up that much space too, because we're creating a matrix of that size. And yeah, that's all there is to it. Let me know if you have any questions. Let me know in the comments below or on the blog. And otherwise, I will see you guys again next week.